Soil condition, all the models somehow they include the effect of soil. Obviously, after, in fact, Loma Prieta, it was very clear that we have to include something about soil condition. It's not, we cannot have uniform attenuation model for everything. So soil nonlinearity is included in 4 models, but soil condition generally is modeled in all attenuation models. Now we have included a new parameter, is sediment depth, which is the depth to the real hard rock, basically, and 3 models include that. There are locations, as like in California, Southern California, that if you have a basin, you have to include that effect also. Now, I'm going to show you only 2 plots. There are literally hundreds, if not even thousands of plots like this, but I want to show you only 2 of them. There is a point that I would like to make. Residual by definition is the difference between what you record, what you observe, and what you predict in the model. What you observe minus what you predict, basically, in a simple manner. In this plot, there are 64 points, representatives of 64 earthquakes, but the one that I really like to emphasize is that right-hand side green dot that you see. That is the Taiwan earthquake, Chi-Chi earthquake. We went through really months of discussion with the USGS and others that, now I'm going to get into that the new attenuation models, NGA models, result in generally lower ground motion. And the issue was that since we have included foreign data like Chi-Chi earthquake in Taiwan, so we are really matching the foreign data. How do you know that we are not missing the California data, for example? This graph shows that green dot, basically, we are not matching Chi-Chi. Chi-Chi earthquake, which was very well recorded earthquake with 400 recording stations. We just want to make sure that we are not matching Chi-Chi and we are not missing anything in California. So that was one of many, many plots that we had and we submitted to USGS and others. That doesn't show you much, but it just shows that the attenuation model relatively works well. There is no any trend. There are thousands of dots in this plot. The results, I'll show you only a couple of slides. This is spectral displacement versus period. It goes from a very short period all the way to period of 10 seconds. I mentioned that the new models, we go all the way to 10 seconds. There are lots of demands for tall buildings, flexible structures, that the period goes all the way to 6, 7, 8. And we have seen also 10 seconds period. So this is new, basically. The other thing that this shows, and it confirmed decades of the research by Chen and others, is that the shape of the spectrum that you see, the shape of the spectrum is a function of magnitude. The dashed line lower one is for magnitude 5. The top one is for magnitude 8. It's very obvious from this that you cannot take one of them and just scale it up and down to match other magnitude. The shape of the spectrum is a function of magnitude. We have to include the magnitude for the shape of a spectrum. This is another confirmation of previous studies. Comparison with the comparison of NGA models. Now I mentioned we have 5 NGA models, 3 of them adopted by USGS. This plot is a spectral acceleration. For the left one for magnitude 6.5, for the right one is magnitude 7.5 for the strike slip. 5 models. Not much different. They are not much different for strike slip fault. But once you get to truss fault, because now more parameters are being involved, more modeling issues are involved, the 5 models are different. So because that's another issue that said, oh, all the 5 models or 3 models of the NG are more or less the same. They are close when you have a strike slip fault. They are relatively very different if you get to the truss fault and other hanging fault issue, hanging wall and footwall issues. Impact of the NGA. Once we were close to finish the NGA in 2006, 2007, 2008, basically, we had numerous meetings with the U.S. Geological Survey. USGS assembled a national team of experts. They call it Tiger Team. They came here many times, face-to-face meeting, and then communications and exchange of question and answers with hundreds of pages, basically. Eventually, USGS, after comprehensive reviewing of the database and the models and everything, adopted NGA models, and they used the NGA models for 2008 hazard maps that Rick also mentioned. Now the change. The change of the national hazard maps from 2002 version that USGS had to 2008 version. These are two maps that are coming from the USGS. The left one is for period of 0.2 seconds. The right one is for period of 1 second. If on the left, you see there basically the difference between 2008 and 2002 values are not much. Basically, everything is plus minus 10%. Not much difference, basically. The right-hand side, you see, this is the west coast of the U.S., obviously. The right figure for period of 1 second, you see lots of blue lines. So it means there are substantial reductions in the estimation of ground motion for the west coast of the U.S. In order of 20, 30, 40%, at least in the California side, depending on the various parameters. So there is a substantial reduction in the estimation of the ground motion. Why is that? There are basically two reasons. I borrowed this slide from Art Frankel, who was with USGS in Colorado office, now moved. Basically, there are two reasons for the reduction of the estimated ground motion based on NGA. One reason, simply, I should say that 2002 national hazard maps were conservative. In NGA, we shaved that level of conservatism. I don't go to the detail. The site condition and soil condition and so on were involved. 2002 national hazard maps were conservative. By NGA, now that we accurately model the soil condition, we shaved that conservatism. That's one reason. Is almost half of the reduction is due to that. And the second half of the reduction is that we have now huge ground motion database, we have a better models, and so on. So that is really the summary of why we get lower ground motion. A strength of NGA models, there are lots of things that I can mention, but I would like to emphasize only 2-3 of the key points. Quantity and quality of the data. I mentioned the database size increased by factor of 3. Really, we have strong and large and comprehensive database. Quality of the data, we checked it and checked it and checked it, and we spent lots of time and money just to make sure that the metadata are okay, basically. Then the models were not only a simple revision of the old models. Basically, we started from scratch, from really scratch, magnitude scaling, distance scaling, all the components. We had serious interactions among the modelers, the NGA attenuation modelers. Previously, I was saying previously we were competing, but we were not talking among each other. Now we are competing, but at least we talk with each other. And that created really a good quality. The quality of all models went up by lots of interaction meetings, 2 a.m., 3 a.m. Meeting with the modelers. Quality literally went up. And also the final thing is the USGS review panel. For the first time, very comprehensive national experts got together and reviewed